Okay, so in this problem, we're using the idea of the relationship between torque, moment of inertia, and angular acceleration. So in this problem, we're talking about a flywheel. So a flywheel is used, it's usually the idea is that it's a heavy disc or a wheel. It could be like more of a hoop shape that is made to rotate really quickly. Like you kind of put energy into it to get it to rotate. And because it has a relatively high moment of inertia, it'll stay rotating and it kind of can be used to store energy. So that's what that wheel is. So in this problem, our flywheel is the gray thing, and we're using a motor right here. You can see what the belt is being used to help get that flywheel rotating. And so we're going to base our problem on this scenario. We're told the moment of inertia of the flywheel is 9 kilograms per square meter, times square meters. And we want to bring the flywheel from 1200 RPM to 1500 RPM in 10 seconds. So in this problem here, they're giving me some information about alpha, but I have to find it. And I can't use RPMs, which is revolutions per minute, as a unit to work with. So I need to do a unit conversion. So 1 revolution is 2 pi radians. In 1 minute, 60 seconds. That will change this into an angular velocity. So 125.7 radians per second. I can do the same thing with 1500 revolutions per minute. It's going to change into 157 radians per second. So this is omega initial, this is omega final. My alpha is going to be my change in omega over my change in time. So I'll do 157 minus 125.7. I want to do that in 10 seconds. And this is going to give me an angular acceleration of 3.13 radians per second squared. Now I want to know what torque do I need to get this angular acceleration. So I'm saying torque is I alpha. I know what my moment of inertia is 9 kilograms meters squared and 3.13 radians per second squared. And so my torque is going to end up to be 28.17 Newton meters. So basically, if I apply a torque of this magnitude, I can achieve the acceleration of the flywheel that I desire.